Dear all, my name is Levent. I'm a PhD student in TU Berlin, and the title of my talk is Polynomial Time Algorithms in Invariant Theory for Torus Actions. This talk is based on a paper with the same title, and it is a joint work with Peter Birgeser, Visumakka, Michael Walter, and Abe Victorson. So I would like to start by giving a list of equivalence or isomorphism problems. In the first glance, these problems have no connection whatsoever with each other. However, they are connected by the frame of geometric complexity theory. This first example is the well-known graph isomorphism problem. Given two graphs on n vertices, we want to decide if they are isomorphic. The second example is the rational identity testing in non-commuting variables. We are given two formulas with division gates, phi and psi, but the variables of the formulas do not commute. Then we ask whether these two formulas are the same. So this is like the non-commutative analog of polynomial identity testing. As an example, we have this formula over here on the left, which actually equals 0, though it is certainly non-trivial. The third example is the matrix or tensor scaling. We are given two n by n matrices, A and B, and we ask if we can scale A and obtain B. Here, scaling means that I am allowed to multiply A from left and from right by invertible diagonal matrices. The fourth one is the modular isomorphism problem. Are two given modules isomorphic? The next one is the famous tensor ring and border rank problem, here stated as a decision problem. Given a tensor X, is the rank of X smaller than R? Or the approximate version, is the border rank of X smaller than R? Lastly, another related problem, the determinantal complexity of polynomials. We are given a polynomial f and ask if its determinantal complexity smaller than R. The determinantal complexity of f is the smallest n, such that f is the affine projection of n by n determinant. There is also the approximate version. Can we write f as the limit of affine projections of the determinant? So these problems are actually all instances of certain orbit problems that we will discuss in the talk. The setup is that we have a group G, we have a vector space, and the group G acts on the vector space by invertible linear transformations. So the standard example is the action of the symmetric group on n-dimensional vector space by permuting the coordinates. So this captures, for example, the isomorphisms of graphs. Symmetric group permutes the vertices of a graph and produces an isomorphic graph. We define the orbit of a vector as the set of all vectors that we can reach from V by applying group elements. We denote the orbit by O sub V. This is the first object of interest. So this vector space admits the Zariski topology, and we denote the Zariski closure of the orbit by OV bar. All problems that we have listed before can be seen as instances of these following three problems. Say we are given two vectors, V and W. We ask whether the orbit of V equals the orbit of W. We call this the orbit equality problem. Secondly, we ask whether the closures of the orbits of V and W intersect, orbit closure intersection problem. And lastly, we have the orbit closure containment problem. Is the orbit closure of W contained in the orbit closure of V? So these complexity classes of these three problems are subject to a vast literature. For example, by Blazer et al., we know that orbit closure containment problem is NP-hard in general, whereas the orbit closure intersection problem, it is believed to admit a polynomial time algorithm. And the main result of this talk is that all three of these problems admit polynomial time algorithms when the group G is a torus. So the actions of tori, which is plural of torus, correspond to a class of actions that we call the scaling actions. Scaling actions are the ones where we scale each coordinate of the vector with a monomial of some fixed number of scalars. So let me give some baby examples to show how they work. In the first example, we have only one scalar. We multiply the first coordinate with t inverse and the second coordinate with t. And then there are four types of orbits. So there are hyperbolas, and there are, of course, infinite many of them. And also notice that each hyperbola is a closed set. There are the axis lines, the x-axis and the y-axis, but excluding 0. And the last orbit is 0 itself, marked yellow. In the second example, both coordinates are multiplied with t. Then the orbits are lines through 0, excluding the 0 vector. Again, 0 is an orbit itself. In the last examples, we have two scalars denoted s and t. S is multiplied with the first coordinate and t is multiplied with the second coordinate. And there are four orbits. One orbit consists of vectors having non-zero coordinates, the shaded region. And then there are the x and y axes, excluding 0, and then there is 0. Okay, let's formalize that. A torus is the default direct product of the multiplicative group of the field, where D is a natural number. It is called the rank of the torus. This rank also coincides with the dimension of the torus as a variety, but we keep the term dimension for vector spaces to avoid confusion. And a note for maybe the expert audience, this tori happen to be precisely the class of reductive commutative connected groups. A scaling action of a torus T on the vector space is an action of this simple form, small t times the vector, is obtained by scaling each coordinate with a non-zero scalar. These non-zero scalars are determined by integer vectors of size d, which are the exponent vectors. We call them weights. So each coordinate has a weight, and the coordinate is multiplied with this Laurent monomial given here. The product t1 to the omega I1, t2 to the omega I2, and so on. So this presentation of the action allows us to encode the action as an integer matrix called the weight matrix of pi. So this weight matrix is defined as the matrix having weights as its columns. And important, up to applying a change of basis, all actions of a torus, they are all of this form. So now let's recall the problems of interest. We have a torus of rank D and the scaling action on the n-dimensional vector space. And this action is encoded as the weight matrix M. And given vectors V and W in the vector space, we want to decide, first, are the orbits of V and W the same, orbit equality? Two, do the Zariski closures of V and W intersect, orbit closure intersection? And three, is the orbit closure of W contained in the orbit closure of V, orbit closure containment? And the main theorem of this talk is that each of these problems admit polynomial time algorithms. And to be more precise, each algorithm takes M, the weight matrix, as the input. The weight matrix is encoded in binary. The entries of the matrix are encoded in binary. And the algorithms take two vectors, V and W, again encoded in binary. So we assume that the entries of V and W are Gaussian rationals. And we assume that the maximum of the bit lengths of the entries of the matrix V and W, they're all bounded by B. Then in poly D and B time, we can decide all three of these problems. So, okay, now let's talk about that. One way to separate orbits or orbit closures is to use invariance, as hinted in the title of the talk. So the action of T also induces another action of T on the polynomial ring with n variables. And an invariant is a polynomial f, such that f is constant on each orbit. So namely, f of v equals f of t times v for all t. So the invariants form a subring. We denote this subring by putting a superscript t on the polynomial ring. Now, this is a well-known theorem in geometric invariant theory, Mumford's theorem. It states that two orbit closures intersect if and only if every invariant f takes the same value on v and w. And this theorem holds for any reductive group acting on a variety, not only a vector space. And our next result is that if two orbit closures do not intersect, then we can, in polynomial time, construct an arithmetic circuit C, which produces an invariant that separates these orbits. However, I will not talk about the proof of this theorem. Now, there is this big literature on these invariants or how to produce them computationally, and there are several hardness results on this direction. So for this reason, we used rational invariance instead of polynomial invariance, and we consider the split as the main novelty of our paper. So let me compare polynomial and rational invariance and explain why rationality was so useful for our purposes. So a polynomial invariant, it's a polynomial that is constant along orbits. In the case of the scaling action, so these invariants are spanned by invariant monomials. A monomial, say x to the alpha, it is an invariant if and only if the weight matrix M times alpha is 0. But here's the thing, this set of invariants, or equivalently these exponent vectors of invariant monomials, they form a semigroup. So all alpha, entries being natural numbers, such that M alpha is 0. So semigroups are, so they are okay. So they admit a finite set of generators, and there is this unique minimal set of generators, Hilbert basis. So we have a finite set of generators for the invariant ring. And it is enough to check equalities for these generators to decide orbit intersection. But there's the problem. So this Hilbert basis of a semigroup, it might be exponentially large with respect to n. So this is our first hardness result for invariance of scaling actions. Now, let's consider this conjecture by Malmolay. So Malmolay proposed a way to represent invariance. He proposed that let's find an arithmetic circuit, polysize, in two sets of variables, x and y, such that if I insert numbers for the second of set of variables, that would give me some polynomials in X. And I want these polynomials to be a generating set for the invariant ring. And sad news is that this is not possible. There is a counterexample by Garg et al. The example goes as follows. We consider threefold product of diagonal n by n matrices of the determinant 1. So this group, which is also a torus, it acts on the three tensor product. And what are the invariants? So the invariants, or a generating set for the invariant ring, it is hard to describe, but let's just consider invariants of degree n. So this n is the smallest degree that can occur for an invariant. So these invariants of degree n, they are spanned by a special set of monomials that are called 3D matching problems, 3D matching monomials. They correspond to the perfect matchings of the complete tripartite, three-uniform hypergraph. So if I would take twofold product, the same would happen. The monomials would correspond to the perfect matchings of the complete bipartite graph. And the result of Garg et al. Is that the existence of such arithmetic circuit in Malmoley's conjecture, it would imply some collapse in the polynomial hierarchy. So now let's compare all this with rational invariance. Instead of polynomials, now let's consider rational functions. Reminder, a rational function is the ratio of two polynomials. And we define an invariant rational function the same way. Phi is an invariant if phi of v equals phi of t times v, unless phi is not defined at v or t times v. I will talk about this later, but rational functions are not defined on the whole space. More explicitly, they are not defined at the zero loci of the denominators. So these invariants are, again, generated by invariant Laurent monomials. Laurent monomial is a monomial, except we allow negative exponents. So again, x to the alpha is an invariant if and only if m alpha is 0. And here's the comparison. In the invariant case, alpha lives in natural numbers, the semigroup. Here it lives in the integer lattice. And the kernel of m, the integral kernel of m, inside this lattice, it's a sublattice of the integer lattice. And what is nice about lattices is that they admit a basis, or a lattice basis to be more precise, and the cardinality of this basis equals the dimension of the lattice, in this case bounded by n. And again, so it is enough to check equalities for rational functions only for these lattice spaces. Okay, now let's continue the comparison. We mentioned Malmoley's conjecture. So again, we have a scaling action. And if we have this result, instead of invariance, if you want to compute the generating set for the invariant rational functions, then you can do that in this way. So basically, we can produce in polynomial time an arithmetic circuit with divisions so that we can have rational functions that produces a generating set for the invariant rational functions. So I want to strongly emphasize that this result holds for scaling actions. Okay. So why does that happen? Let's continue the example. So the same action. On the left, we have polynomial invariance given by 3D matchings. On the right, we have rational invariance. So having denominators means that we can add and remove edges from matchings. So we define these flip operators, or equivalently cycles of length 4. So it is hard to picture it in 3 dimensions. So consider bipartite graphs and perfect matchings. Say you have two edges like this in the perfect matching. You remove them and replace it with the cross. So this is called a flip operation. The thing is, starting from one perfect matching, you can obtain all the rest by applying these flip operations. So therefore, a generating set of rational invariants is one single 3D matching and the flip operators. So I would like to point out that on the left, we have n factorial square many invariants. They're all members of the Hilbert basis. On the right, we have polynomial in n many invariants. So there is this advantage of using rational invariants, but there is no free lunch. Let's consider this example from before. The action of rank 1 torus on the plane by scaling vectors, the orbits are lines. The invariant ring is trivial. Why? That's because all our width closures intersect at 0. So therefore, there is no way to separate them. But the field of invariance, it contains this special invariant y over x, which is the slope of the line. So it does separate orbits. However, it only separates orbits at which it is defined. So if x is 0, then the invariant is not defined. So this invariant does not separate the y-axis and the orbit of 0. So, and the upshot is that the rational invariants, they're good at separating orbits, but they only separate orbits when they are defined. So we need to be careful about where our Laurent monomials are defined. So we consider this variety, vectors with non-zero coordinates, and X is stable under the action of T. And more importantly, Laurent monomials are defined on X. And there is this one more property of X, which is that the orbits in X are closed with respect to the subspace topology. Like pictorially, if I take a limit inside an orbit, then it must derive at least one coordinate to zero. If it does not derive any coordinate to zero, then you did not leave the orbit. So this property, it works like a charm because now we can apply Mumford's theorem. The invariants separate not only orbit closures, but they separate orbits because the orbit closure and the orbit, they are the same. So the corollary is that we obtain two orbits are the same if and only if every invariant Laurent monomial assumes the same value on the orbits. So perfect. This is almost an algorithm for orbit equality. But now we must ask, we can separate the orbits in X with Laurent monomials. What about the orbits outside of X? So for simplicity, I will assume that the multiplicity of each weight is 1. So every weight occurs exactly once. And then we define the support of a vector as the set of weights that occur in V. So it should be clear that if two vectors do not have the same support, then they cannot have the same orbit. Now say S is the support of V. Now delete all columns of M weight matrix outside of S. So only the weights of V stays. Now compute a lattice spaces BS for the integral kernel of this new matrix. So in this lattice spaces, we only have exponents of Laurent monomials that are defined at V. I mean, I make sure of that because I just ignore the variables xi where vi is 0. And I claim that if I take the Laurent monomials with exponents in these lattice spaces, then they're enough to separate the orbits with this given support. So takeaway is that I just ignored the 0 coordinates of V and I did things as if every coordinate is non-zero. Okay, now we can actually give the algorithm for orbit equality. So my input is the weight matrix M, two vectors V and W. So at the first step, I check if they have the same support. If they do not have the same support, the orbits are different, I am done. If they are the same, then I delete columns of M outside of their supports and compute a lattice spaces B. Then for each basis element, I check if the corresponding Laurent monomial, x to the alpha, takes the same value on V and W. If they all take the same value, then the orbits are same. If not, then they are not the same. And this is the algorithm. But I did not explain these two steps. One, how do we compute a lattice spaces? And two, how do we check if two Laurent monomials are the same? So, okay, let me explain that. So there are many algorithms that produce a lattice when given a matrix M. So we went with the Smith normal form. If you give me M, then I can multiply M with invertible integer matrices from left and right to diagonalize it. And there is this algorithm by Kanan and Bacham, the Smith normal form, and these multiplier matrices on the left and right, they can be computed in polynomial time. And so this was how we computed the lattice spaces for M. Basically, the columns of W, the right multiplier matrices, matrix, with index r+1, r+2, up to n. These columns gives a lattice spaces. Okay, now let's explain these Laurent monomial equivalents. Of course, it is not feasible to actually evaluate this Laurent monomial. So if the bit length of V is B, and if the bit length of the exponent is again B, then the number is in the order of 2 to the B to the 2 to the B, which is exponentially large. Still, it is possible to check if two Laurent monomials are the same. This technique is, so that the proposition is relied on this technique of factor refinement. You pick something from left, something from the right, take the greatest common divisor and quotient it out and repeat. So I will not explain the details, but still let me mention, so there is a generalization of the proposition to arbitrary number fields by Guy. In particular, we can also decide orbit equality in polynomial time if the entries of the vectors are given from some fixed number field K. Okay, so this was the solution for orbit equality. Now I move on to orbit closure intersection problem. So what I want to show is that there is a polynomial time reduction from orbit closure intersection to orbit equality. So this follows by this well-known fact from geometric invariant theory every orbit closure contains a distinguished orbit, namely there is a unique closed orbit inside every orbit closure. So this property of the unique closed orbit is that two orbit closures intersect if and only if these two unique orbits coincide. So this gives a reduction. Instead of orbit closure intersection, decide if the orbits of these two unique closed orbits are the same. If we can actually compute this unique closed orbit in polynomial time, this would give me a polynomial time reduction. So there is this nice description that I want to explain in terms of polyhedral geometry. So given a vector v, I define its Newton cone. It is the real cone generated by the weights of v. And this is a convex cone, and it has faces. What we will do, we will assign to each face an orbit in the orbit closure. Okay, say f is a face of v. I define v sub f. So the ith coordinate of v sub f is v sub I if the ith weight lives in the face, and it is 0 otherwise. So it's like restricting v to the face. And the theorem is that there is this map sending each face f to the orbit of v sub f. It is a bijection between the faces of the Newton cone and the orbits inside the orbit closure of v. So this map has one more property. If the face f is contained in the face f prime, then the orbit of v sub f is contained in the orbit closure of v sub f prime. Okay, so this theorem apparently is well known in the world of toric varieties. So we have the faces of the Newton cone and the orbits inside the orbit closures. But what we want is the unique closed orbit. So which face gives us the unique closed orbit? So there is a special face of a cone that is called the linearity space. The linearity space of a convex cone C is the largest subspace contained in C. So if LV denotes the linearity space of CV, the Newton cone of V, then one, the linearity space is actually the smallest face of the cone, in the sense that every face of the cone contains the linearity space. And two, as expected, this linearity space corresponds to the unique closed orbit. So the orbit of V restricted to linearity space is the unique closed orbit inside the orbit closure of V. Okay, I want to mention we can construct this V sub LV in polynomial time using linear programming. So the ith coordinate of V sub LV, it will be VI if minus omega I, the ith minus ith weight, it is in the cone. If it is not in the cone, then the ith coordinate will be 0. So this gives me a way to construct it. Okay, let me give an example first, then I will explain why this bijection between faces and orbits happen. So consider this rank 2 scaling. We have S, we have T. The first coordinate is multiplied with S, the second is multiplied with T, and then let's take the vector 1, 1. So on the left, we have the vector space, and then there are 4 orbits. The pink region, it's a 2-dimensional orbit, and then there are 3 orbits in its closures. In its closure, the x-axis, the y-axis, and 0. And on the right, we have the Newton cone of 1, 1. It lives in Z2. So this cone, it is spanned by the weight of x, 1, 0, and the weight of y, 0, 1. So the cone is the positive quadrant. And again, this positive quadrant has 4 faces. The cone is a face of itself, and it corresponds to the 2-dimensional orbit. Then there is the blue face on the bottom. This face only contains the first weight. So what happens if I restrict my vector to this face? The second coordinate vanishes, and I obtain this vector 1, 0 on the left, which gives me the blue orbit. So blue face goes to blue orbit. Similarly, purple face goes to the purple orbit. And lastly, there is the yellow face consisting of only 0, and it is the linearity space. So there are no weights in this face. Therefore, it corresponds to the 0 orbit, the yellow orbit. And notice that the orbit of 0 is the only one among these 4 orbits that is closed. So, okay, let me now explain why this bijection between faces and orbits happens. So we define a 1-parameter subgroup of the torus. It's a map from the multiplicative group of the field to the torus. And it is of the form epsilon maps to The first coordinate, epsilon to the some integer, second coordinate, epsilon to the some integer, and so on. By an abuse of notation, I denote the map and the vector of exponents, mu1 up to mu d, by mu. So the mu it's an integer vector, also interpreted as a map. And this map gives us a curve inside the torus, and hence the name one parameter. So now the weights, which are maps from the torus to the multiplicative group of the field, and we have one parameter subgroups, maps from the multiplicative group of the field to the torus. So they both form integer lattices, and these lattices are dual to each other. There's a pairing among them. So take a one PSG, mu, take a weight omega, and then compose them. So composition will be a map of the form epsilon maps to epsilon to the k for some integer k. So this k is the pairing of one PSG and the weight. It also equals the inner product of mu and omega. So here's the thing. In the Newton cone, we have weights as vectors, as generators. And by this duality, the one parameter subgroups, they will correspond to the hyperplanes in this space. So okay, let me be more precise. There's this theorem, Hilbert-Manford criterion. If I have a vector v and a vector w in its orbit closure, then I can reach the orbit of w as the limit of a one parameter subgroup applied to v. So mu epsilon is a group element. Then I apply it to v. So as I move, epsilon goes to 0. I move in the group. So I apply it to v. So I move in the orbit, and in the limit, I reach an orbit in the orbit closure. So this criterion says that I can reach every orbit with a one PSG. So here I want to remark, to avoid confusion for people who are familiar with these things, for general groups, this would only hold if the W is the unique closed orbit. But for tori, this general version also holds. So let's write this limit, mu epsilon applied to v. It's this vector on the right, the first coordinate, epsilon raised to the power mu inner product omega 1. The second is mu inner product omega 2, and so on. And when does this limit exist? It exists if whenever vi is non-zero, then we must have mu inner product omega I is non-negative. So mu inner product omega I is non-negative for every weight omega I in the support of v. Okay, now say limit exists. Then what is the limit? So note that mu inner product omega i's, they're all non-negative. So this is equivalent to the statement that, so if I take H as a hyperplane with normal vector mu, then the Newton cone lies in the positive closed out space. And in the limit, only the coordinates that are on H, they will survive. So the limit equals the restriction of V to the face H intersection the Newton cone. And by the criterion, all orbits are obtained in this way. So okay, maybe let's give a picture. Say the Newton cone is this blue region spanned by two weights, one on the x-axis, the other one is on the skew line. We pick a mu. This is equivalent to picking a hyperplane H, such that the cone lies on one side. The intersection will give us a face. It's F. So as we move mu, we can get other faces as well. So for example, the linearity space is 0, and I can obtain that by taking mu to be 1, 1. Okay. So now I can actually give the algorithm we have explained. So in the first step, we compute these restrictions of V and of W to their linearity spaces. Then I use the orbit equality algorithm. I check if these two orbits are the same. If they are, then orbit closures intersect. If not, then they do not intersect. So this is all I wanted to talk about. And I do not have time for orbit closure containment, but you can always check our paper. And normally this is the place where I get questions, but this is impossible. So I invite you to send us an email if you have any questions. And thank you for listening to me.